Login acceptance.
All right, hello everybody. Can you hear me? So I'm Alex. I'm from HSBC, and wow, this is a big stage. But I'm delighted to be here. I moved to Krakow, this beautiful city, 2 years ago now. Loving it, and really a big honor to be here today speaking at Devoxx Poland. So what am I here to talk about? I want to talk about basically a re-engineering that we're doing of part of our Equities technology stack, and why we're doing that. Essentially, it's the part that deals with so buy and sell orders messages, the throughput of that, and the order message state. I'll talk about, briefly, our business requirements, then talk about what our existing design is and some of the limitations that we have. And then I'll go into the different technology choices that we've decided on to basically improve scalability, lower latency, and better resiliency. So what is Equities electronic trading in HSBC? Basically, whenever you buy or sell an order, share, equity, financial instrument on an exchange electronically, that can either be done as direct market access, when you're sending the order directly to the market, or it can be increasingly now done by an algorithm which is generating these orders which are being sent to the market. Our clients are global that use our Equities electronic trading capability. They love the use of our execution algos, which allow them to place very large orders that are then broken up into lots of little orders with different behaviors based on time or based on volume on the exchange or based on liquidity seeking. We also have our internal traders that sit on trading floors on our big hub locations like New York, London, Hong Kong, Dubai, who use these algos as well. We've been on a journey in Equities technology side for a number of years now, where we've migrated a lot of our technology from more vendor or legacy-based apps to in-house applications. We do that where it makes sense, business sense for both scaling our order throughput and being able to do more orders simply and more exchanges, also to be able to support strategic widget functionality and be more flexible. In terms of the technology teams that are actually supporting this in-house Equities technology development, we've got people around the world, but the stuff that I'm touching on today in particular is being built out of teams based in New York, London, and Poland. So let me talk now about some of the limitations of our current design and why we're looking to do something different. So basically, what we're talking about is the processes and our applications that deal with the order messaging and all the surfaces that need to consume that. And what we have is, let's call it the order management system, OMS. It's written in disruptor pattern, which at the time was a really cutting edge. And it's really designed for high throughput, low latency, asynchronous event processing. It's great because you have, at any given point, data owned only by one thread for write access, which ensures that it's much, much faster. You don't get contention. So the OMS takes in orders, executions, cancel events coming in. It puts it on a disruptor. So this is actually a concurrent ring buffer. And we then deserialize that object. We journal that order to hard disk. We do event replication. And then we have some business processing logic that then typically will then decide where the order needs to be routed to. Puts it in an outbound disruptor, another ring buffer. And then that can get consumed by all of the other services in our system. So that's typically our multiple algo processes that are themselves generating a lot more orders that are then put back onto the input disruptor here. Obviously, we've got services which are actually market connectivity, so two different exchanges to actually trade and send back ACKs and fills. We also have processes that deal with data capture. We use KDB for best execution analysis, very important, highly regulated industry. And then we've, of course, got view servers as well for pushing data to the UI. So, talked about the event replication. Currently, our primary OMS has all of the order flow going through it. So, if something happens during the day and it falls over, we need to have warm backups with all of that state ready and good to go and take leadership and continue. So we actually, to be super safe, we've got 3 backup OMSs here, and it's it's necessary, but it's not necessarily terribly effective, like efficient, because you've got only one OMS that's actually doing work, and the others are just backups. So. Furthermore, so I talked about the falling over of the main primary OMS. What about all of the services that are consuming all of this order event data that's being pushed around? Currently, the way that works is if, say, one of our algo processes goes down, it needs to go to the OMS to say, okay, give me the state of the world, rehydrate me, what's the current state? And that takes time. The OMS is currently written in a very single-threaded manner. It's super fast, but it means that potentially, imagine you have 500,000 market orders and you've got 10,000 paired orders and you've got loads of executions. Potentially, that event to rehydrate state for a process could impact the order flow going through that primary OMS, which is obviously not ideal. So yeah, I talked about how the OMS has essentially become now the golden source for order state, which it doesn't need to be, it's doing too much. We've got processes failover that could potentially slow down order flow, which is an obvious concern if we're looking to scale further. Another thing we have by design is multiple algo processes speaking to that one primary OMS, which leads to natural bottleneck there. So there's some concerns by our business about will we be able to scale further with this design? And then finally, it's not particularly fast. So at the time when we wrote this, in-house OMS, we were happy with it. It was much faster than we had before, but there's necessarily been a bit of code bloat over the years, and there's a bit too much DC, and we can do better, basically. So we're looking to improve that. It's kind of around the low milliseconds currently for some of that key processing. So we want a new design and new technology. We're going to use new technology choices so that we can scale, so that we can have lower latency and better resilience. So how are we going to do that? So first of all, programming language, we're going to choose Java. This is a Java conference. I thought it'd be a good opportunity. No, just kidding. So before, we were actually using Scala, which may be surprising to some. At the time, Scala was actually quite advanced. We weren't too sure where Java was going. It had cool things like lambdas and a few things. But over the past few years, as you all know, there's been a lot of improvements to the Java libraries. And that the reason to choose Scala is no longer so obvious, plus it's harder to find Scala developers. Yeah. The obvious question, why aren't we using C++? So there's actually a really good video on this by Daniel Shaya I recommend you to watch on YouTube, where he basically argues, yes, you can write faster, low latency applications using C++ over Java, but not significantly so. And it comes at a cost. So in particularly the cost of your super bright C++ developers that can write that kind of code. And if you want to be really fast, then actually consider using technology like FPGA, so field programmable byte arrays, where you can directly program onto microcontrollers your specific application logic, or use ASICs, application-specific integrated circuits, where actually at production stage, you build in the logic for your application. So that enables you to go super fast, down to the nanos. You have specialized hedge funds that are into the high-frequency trading business. We're not yet ambitious enough to compete in that space, maybe one day. So Java. For the rest of the presentation now, I'm going to go through the different technology choices we've made. So to increase throughput and scalability, how we've chosen a new design using an event bus command bus pattern with sharding. For performance, I'll talk a bit on the SB binary protocol and some of the GC-free techniques that we use. For lower latency, one of the important things is how do you measure that latency? So a bit more on the techniques there and the hardware that we're using, software we're using. A bit also on the network accelerator that we're using called SolarFlare. And I'll finish with some discussion on the fast message transport, where we've chosen Aeron, which is an open source library. So, new design. Our sequencer process here is basically a much cut down version of what our original OMS process was. The idea is that all it does is listen to events on a command bus, sequence them, so assign them global IDs, journal them on a separate thread, replicate that on a separate thread, and do a minimum amount of business logic, and send that back out on the event bus thread, which you'll see next slide. The point here is any server's component that wants to speak to the sequencer has to put events onto the command bus, and only the sequencer reads events off of the command bus. What's important about the sequencing is that, and why that has to be single-threaded, is you have, for example, two clients want to buy HSBC shares, and they send the orders about the same time. We need to guarantee that the order in which we receive those buy orders is the order in which we process those orders on the exchange. So we must have the sequencing and global IDs in that sense to guarantee that there's no out-of-order processing. So replication to secondary sequencers. The events are then put onto the event bus to be consumed. The bus is multicast, and all of the services listening on the event bus can then listen to what's relevant to them. So what's really key and new about this design is the replay server that we've added here. So remember how previously, if one of our services goes down and needs to rehydrate the state of the world, it had to go to our primary OMS. Not efficient, right? We now have something called replay server, which can talk to the process that has stopped and is restarting. And as it restarts, that replay server can send all of the state that it needs to get up to the point where we are. And then so that's done out of band, so no impact whatsoever to the sequencer process, which can continue doing its thing. And it's smart enough that once the process that's restarted has gotten up to the latest event, it can then cut over to the live stream and listen to the event bus again, so stuff coming from the sequencer. So that's one of the big changes we've got. Then just to complicate the diagram further, I've added a few more boxes. The fixed proxy on the top left there is one of the things that we're rewriting to be super fast and is dedicated to listen to incoming fixed messages, so trade messages, TCP/IP, and then to translate those and put them onto the command bus for the sequencer. Mentioned algo processes. We have a lot of those that are generating orders, so there's lots of those that are sitting on this event bus as well. So what's great about this new design is that it gives us a number of opportunities for scaling this up. We could have multiple services on the same event and command bus, or we could have multiple event buses, same or different sequencers. I've given one possibility here, which we're looking at doing, is you can have one fixed proxy process. So this is listening to client orders coming in. So here we've got two orders, one for selling Budimex and buying Plastbox, which apparently are well-known Polish stocks. What we'll do is we'll shard the symbols by letter. So everything starting by A to N can go to one instance. Everything starting by O to Z go to the other. So hence, Budimex goes left, Plastbox goes right, and we can scale that horizontally quite easily. So we could have multiple of these and just split by instrument. The importance of splitting by instrument is that if we do that, we're guaranteeing again that orders are not done out of process. So all bootmx will go left. So we've talked about how the design, new design will help us with what we're trying to achieve. Now I want to talk a bit about the binary protocol, so all the serialization and deserialization of objects in out of memory, the moving of messages around. It's quite important. So if we're looking for microsecond, handful microsecond level events through sequencer, for example, we need to make sure that the binary protocol we use is not adding unnecessary even nanoseconds to that. We evaluated a few different choices. So in particular, SBE, so simple binary encoding, which we ultimately chose. Also chronicle wire. We also evaluated what it would involve to write our own custom binary protocol. In the end, we decided not to write our own, because if you do that, then your developers have to learn and understand your own custom protocol, which is only used at HSBC. So it's not great. Also, you don't get, so speaking to external teams becomes a lot more complicated as well. Case in point, we're using Velocimetrics for performance monitoring. Out of the box, Velocimetrics gives you standard binary decoders for protobuf, SBE, and chronicle wire. So that made sense to use one of the standard ones. If you want to be fast, you want good performance, you need to have sympathy for your hardware cache subsystems. So you want to make sure that you're working on data that's co-located in memory, and that you then walk around your memory in a predictable fashion. SBE, one of the key design principles, is that it actively encourages and tries to enforce as much as possible using streaming access to data. So directly encode data into buffers in like ascending progression. And then equally, it strongly advises you that you're decoding, that you also write that into, you read the data off the buffer in streaming sequential manner. It uses a flyweight pattern, so that's where an object, to minimize memory usage, will do sharing of similar data, of data amongst similar objects. And it's quite powerful. So other key design principles of SBE are copy-free, so you're not doing any intermediate encoding, decoding. You've got allocation-free, so it tries not to at any time create extra objects or allocation of memory. And it uses native type a lot, so faster memory access. So all of this leads to predictable and minimal variance in performance in your latency, which is great. So that was a good reason to go for SBE. In terms of the integration with transport layer, that was a fairly obvious choice for us. Because we're using Aeron, which I'll talk about a bit further on, Aeron actually uses SBE under the hood. And actually the guys, our industry expert on Java low latency, Martin Thompson, I recommend watching his stuff. He actually co-wrote Aeron, and he co-wrote SBE. So it's definitely good that way. And he wrote it all open source, so like everyone can benefit from it. So what else? Yes, backwards and forward compatibility. This one was a bit more tricky. If you look at product like Chronicle Wire, that was quite good in that it allows you to encode fields in different orders. It allows you to just skip certain fields if you want, which makes it easier to do backwards and forwards compatibility. Also, if we'd written our own protocol, that would have been easier to manage. With SBE, it's a little bit more tricky due to the flyweight pattern that forces you to encode and decode into fixed fields and offsets. We did need support for variable length data, which you could do with SBE. You can define upfront custom length fields. So, for example, if we want to define an order ID, that will always be 20 bytes. You can define that upfront and then use that as a type going forward. So SBE is fairly easy to use. There's a tool called SBE tool, which you basically include in your POM file, runs as part of the build. You define your XML schemas, which then, off the back of that, SBE builds automatically the encoders and decoders. There's an example here of the new order single encoder, and it's fairly straightforward and easy to reason. You can see it's just putting data into buffer with certain fixed offset. So, talked about how the design is going to make it better. Talked about SBE is a binary protocol, which is going to make it better. A bit more on garbage collector-free techniques, and also SBE helps us a lot in this regard. So, OffHeat Memory. The more memory you have on the JVM heap, necessarily the more time your garbage collector will spend dealing with all the objects in memory. And at some point, you have that stop the world event where all threads of your application stop while the GC goes through the heap and all the objects. Yes, there's a lot, as time goes on, the garbage collector implementations you can get now are increasingly fast and much better, but any GC is still bad, so we try and avoid it as much as possible. So using off-heap memory refers to using memory allocated directly to the operative system outside of the JVM. String interners. So string interning is useful when you have lots of strings you're having to deal with. You can create a map. You can put any new string cached into that map. Any string that already exists in the map can be immediately thrown away. That's short-lived garbage, which is the fastest for the GC to process. So it's quite efficient in that way. We didn't use the default Java string.intern function because that's using Java string pools, which does have a fixed amount of memory. So there was a limitation, and if you got too big, you would still get some GCing happening. So we've an acceptable use case where we will have a memory leak because we'll size up front a very large piece of memory, and we'll just keep adding, in this case, order IDs to that map. Obviously, we need to be very careful we size that to the right size, but it's efficient and it helped us optimize for our processes. So interestingly, order hierarchy is one of the things that we have kept on heap versus a lot of the stuff happening off heap for the serialization. Good. SBE highly recommends using off heap buffers. You can actually allocate them at the thread level, so it's quite efficient. Object pooling, fairly well known, where you pre-initialize a certain number of objects and put them into a pool. The client come along, request one of those objects, do operations, put it back in the pool. It doesn't get destroyed, so it's more efficient again, less GCing, and we use that as well. We've got an example new order single event which has an object pool. So as we're reading stuff off the buffer, we can put that into that object, do our processing, continue. So next, I want to talk about time protocols. So previously, we were just relying on network time protocol, NTP, which is defined by the NTP servers at National Institute of Standards and Technology, NIST, right? There's inevitable latency between our servers and those servers. And the other challenge we found is synchronizing between our own servers. So we were able to get it kind of around to millisecond, but we're trying to move into a space where we measure things in microseconds, and that was no longer good enough. So we're now using precision time protocol. That allows you to go nanosecond, even picosecond, apparently, and for synchronization. What we've noticed is that having moved to this for our servers that are co-located with their exchanges, we've gotten down to a 50 nanosecond synchronization, which we're happy with. So, and again, like the performance constraints of the sequencer that I mentioned, we're looking to be kind of a handful of microseconds from command to event. So lots of latency requirements. The key thing is, how do you measure that? So we've got a number of ways. Previously in the past, we were already using lots of writing of latency events to InfluxDB, using Grafana to then show that. More recently, we're now using something called Java Micro Benchmarks Harness, which is good for Java, works with the JVM, and allows you to do benchmarking really on a micro scale, which is great. We've got two examples here, it's kind of test data, but it kind of gives you an idea. On the left, we've got a previous design. You can see a lot of noise, and you can see that we're kind of in milliseconds area, low milliseconds. And on the right, this is some testing for some of the sequencer threads. So event in, event out, how fast is that? And it's more stable and down to kind of handfuls of microseconds, handful microseconds. And it's not really a fair comparison because the sequencer on the right is not doing as many things, and there's still going to be a bit more business logic to add as we continue. But we will still target at the 90th percentile to be under 1 millisecond for that. So. Velocimetrics, recently bought out by Beaks Software a year ago. This is quite interesting. It allows you to monitor end-to-end latency in all the network hops. So you can see all the wiretaps here all over. So we've got an fixed order coming in, TCP/IP. We can, Velocimetrics or Beaks can read that off the wire before it goes into our fixed-in component, then do some translating before it sends that out to the command bus. And again, we can measure that, so 0.2 points. We can do, again, the same thing off the command bus before it goes into the sequencer and out of the sequencer before it goes to the event bus. So it's really useful to measure all of those things and to get the wire-to-wire view. So starting from your order that's coming in from your fixed client all the way to getting to your, in this happy acre mock here, but it will be your fixed exchange. So actually going to market, and how long does that take? And then equally, when you get a response from your fixed exchange, whether you've had a fill on that order or it's been canceled or rejected, how long does that take to go back through all of the hops? Beaks also gives you something called AppTap for application metrics. So they call it ring the bell, and it means that you can also, at application level, say in the fix in here, we've got our Chronicle fix coming in. We need to translate that to SBE, right? How long does that take? We can then call into the Beaks API and write that latency and see how that looks over time and for multiple orders, etc. So it's really quite useful, quite powerful. Here's the UIs are quite good. Here's just like a heartbeat latency distribution. You're on the top here. We can see that at 99.99% percentile, we're something around 12 microseconds for this test here, which is pretty decent. And below we've got at the 99.99th percentile for a sequencer thread that we're testing here, we can see that we're mostly staying below that 20 microseconds, which is a good start, but obviously we'll keep working on that. The other view you can get is actually order by order. So all of the different events, what exactly is the latency that we see on that, which is really useful if you want to look at outliers and then like zoom in on them and why is that. I forgot to say, so what's really interesting when you're looking at the latency benchmarking is, what is your maximum performance? Like what if you have a huge message burst of orders during the day? What's the maximum you can do before you start seeing some back pressure? Or what is the minimum partition size of the disk that you need to measure up front so that for an expected, maybe big volume message during the day of orders, you're not going to run out of disk size. So all of those things are important. And also, over time, if you're doing a software upgrade, a network upgrade, performance optimization, or you've written some code which is not performant, you need a way to be able to monitor that latency and how it evolves. Maybe I don't want to check that code in, I want to revert it. So you can actually make a decision actually based on latency and compare it to previous. So again, it's really important to be able to measure these things. So now a bit on network accelerators. So we're using something called Solarflare, and this achieves extreme low latency by a combination of kernel bypass, specially designed hardware, and optimized drivers. It maintains application compatibility and support for TCP/IP, so you don't need to make any changes to your messages. It's very easy to use. So these days, our network cards are increasingly sophisticated and can manage a lot more order throughput. What's actually the limiting factor is your Linux kernel and how it talks to your networking stack. So what Solarflare has is a library called Openonload, which does this kernel bypassing. And essentially, it works around the Linux kernel by implementing all the network stack in user space. So you can see here a typical network card and your receiving queues. Openonload will actually define hidden flow steering rules and take some of that data and send it through this other hidden queue and that user space, which will directly talk to the networking components then afterwards. So it's quite cool that way. It's also quite easy to use. We, to be honest, haven't done a lot of changes in terms of what you get out of the box. You kind of defined a latency profile that you want. You turn it on. You tell your application to run with it. If the hardware is turned on, it will just run. And we found that we were able to shave off a few microseconds off of some of those key events, which was significant for us. So it was good. So we've talked about a lot of things. The design, SB binary protocol, how you measure latency, talked about Solarflare. Let's end with Aeron now, which is our really fast message transport layer that we're using. Open source library, again, written by Martin Thompson. It's OSI layer 4, designed for high throughput and low latency. It provides reliable flow control transition over UDP, unicast and multicast, as well as ultra-fast inter-process compute on the same box. So I've taken this diagram from Martin Thompson's presentation. He will explain it far better than I will, but some of the key things that I find interesting. So you've got clear separation of concerns between your client application of your publisher, subscriber stuff, the actual media driver that is just dealing with byte shuffling, just moving data around, goes over your media, which here is for us, is our UDP multicast. And then you've got the receiver end, again, media driver just dealing with receiving, and then your client, which actually does the logic, which does the subscribing and reading off. So Aeron uses dedicated log buffers, so large shared sections of memory. And it's super fast because basically that sender, conductor, and receiver can be 3 different threads. And if you're wondering what that conductor is, it's for all the kinds of events that don't happen very often. So you have your new user connection, your new subscription, maybe doing some cleanup in the background of the log buffers that the sender's no longer using. All of that can happen kind of in the background by the conductor thread, which speaks to the sender, puts things on a queue. It doesn't need to be super fast, and the sender can just then be dedicated to just moving data, bytes across the wire. So that's quite interesting. Also, Aeron uses Agrona data structures, similar to SBE, and that allows you to have key by native types, which is faster, and it avoids the boxing, so that the allocation of objects is good. We're currently live with Aeron, using it in colocated data centers. Obviously, when you're in the business of electronic trading, the closer your servers are to the exchange, the faster you'll be. So we have, not for everything, we have a number of markets where we have servers colocated with exchanges. And we use Aeron there in multicast mode. Aeron has a really good handling of back pressure, flow, and congestion control, which is consistent with command and event bus architecture that we require. basically, our sequencer is designed to be really fast. So we're not too worried about not being able to put data onto Aeron fast enough. But if the log buffers start, filling up and there's an issue with too much pressure, Aeron is smart enough to tell the sequence, say, I'm now in back pressure mode. That process can then decide what to do with that. Does it slow down, stop, does it wait for later, which is quite useful. So I mentioned that both SB and Aeron are using Agrona data structures. And given we want to deploy Aeron also on campus, we will also need to support a multi-destination unicast approach, and Aeron will allow that. So looking into that. We can't do the multicast on campus because we have a fairly flat network in places, and we don't want to risk have any UDP multicast storms flooding our networks. So important to keep an eye on that. So yeah, that's kind of a whirlwind tour through what our previous design was for this order messaging platform, what our new design is, the cool technologies out there you can use now in Java for writing super fast applications. And there's some good links I've put here to some videos. So one is on Aeron by Martin Thompson. The other is how low can you go, I mentioned. So this is about the whole C++ versus Java and the pros and cons, and his arguing that Java is indeed fast enough. And then there's lots of documentation. A lot of this stuff is on GitHub. Yes. So any questions for anyone? Sure. Yes? Yeah. Well, we have multiple sequencers. So if one becomes unavailable, it will immediately it's warm and can pick up. We actually, that's a really interesting point you touch on. Because we're writing to journal and we're replicating in separate threads, we are actually prioritizing throughput over recoverability for that very small amount of events which might not get journaled. So that is something actually it's a kind of a heated debate and something we'll be continue to consider, and maybe for different use cases. So Aeron gives us a lot of that. So yes, it's multicast, so lots of stuff can get lost. But Aeron will manage that on the receiving end and give you information, give the processes that are listening information on whether the data is there or not. And because it's all done on a separate thread with the conductor and it's off of the main sender and receiving threads, it's not slowing anything down. But yeah, basically Aeron does that for us. Yes, yes. So we're not using bare metal for everything, but we're using bare metal where we have the hot spots for latency, right? So everything that has to do with that order going to exchange and back, that has to be, well, we've chosen to be bare metal. But for other things that don't need to be quite so much, like doing some pricing of something that can come back in a few milliseconds later, that can be done on JVMs or virtual machines. Absolutely. So it's not only bare metal, but for the fast stuff, yes, bare metal. Good question. I'm not sure which DC we're using. If you want to connect with me afterwards on LinkedIn, I'll find out. I've sadly not had the opportunity to actually be hands-on development in this, so I'm just working with the developers to get to, which is still interesting for me, but I don't know. So let me answer later. Yes? So I saw a video by Martin Thompson who said that Aeron is, I think, something like 20 times faster. He was saying of course, Aeron is far, far fast. So it's not, multiple orders of magnitude, but in that video he was saying it was 20 times. Yeah. Yeah. Yes. Yeah, yeah. Well, we have. Yes. Yes. Well, there's heart beating and there's messages going back and forth to to atomically make sure that that does happen. The important thing is that we keep it off of the main threads that are actually dealing with moving the order through our stack. But if you have something more specific, I can try and find out for you. Yeah. All right. Thank you, everyone. It's been a real pleasure.